Two traces routed together on a printed circuit board can transfer energy between them through the electromagnetic field coupling between them. We call this crosstalk. The amount of crosstalk depends on different layout factors, how far they are spaced apart from each other, how long they run in parallel to each other as well, and also dielectric properties in the PCB. The way to calculate crosstalk is not to estimate it from the layout rules, but you have to calculate it. So why does crosstalk matter? Why is it a problem? It is a signal integrity problem, one of the 9 top signal integrity problems you need to know in PCB design. What happens is when you have one signal trace and another signal trace, one signal trace has a signal that it's sending from one chip to another that you don't want the voltages, you don't want anything to interfere with that signal. Let's say you're supposed to be sending 1.7 volts or 1.1 volts, 2.2, 3.3 from one chip to another chip, and a chip that's receiving the signal expects to see that voltage. But then you have another trace, let's call it trace B. Trace A is the initial trace, and trace B is the second trace. You bring trace B close to the trace A, and if it has electromagnetic fields coming off of it, then it can interfere with trace A's signal. That becomes a problem for the receiving chip for trace A because then you're distorting the signal, distorting the voltages, and the chip doesn't know what voltage it's receiving, or it's receiving a voltage that's outside of range of its operation. That is a huge signal integrity problem. If that persists, then you're going to have bit errors, miscommunication between chips, and devices not working. Now, that is a major problem because that defeats the whole purpose of making a printed circuit board. So what can we do here? The cleanest way, the best way to figure out how much crosstalk you have is to run it through a simulation. It is a little too hard to calculate for every single trace scenario. So in this video, I'm going to show you the process, the procedure I use to calculate the amount of crosstalk and solutions to the crosstalk problem. In Allegro X PCB layout, we have many traces on this printed circuit board, and I'm going to identify two traces that'll be P0 USB underscore D2 and P0 USB underscore D3. We see that these traces are relatively close to each other. I want to see how much crosstalk occurs, if any, between this signal trace and the other. So what I'll do is I have this thing called the Analyze Workflow Manager, and this rides on top of the power of Sigrity X Aurora. Sigrity X Aurora gives you options like doing a coupling workflow to see how much coupling or electromagnetic field coupling is going on between signals on your printed circuit board. Once you do that, then I can check and see how much crosstalk is happening after coupling is calculated. I'll wait for this simulation to finish and see what results we get. All right, so the simulation is finished. What I did was I ran the simulation on all the nets on this board. Now, that is not necessary for you to do. I just ran it on everything so I could, just see how any of the two traces are coupled whenever I want to. Now let's take a look at viewing the coupling visions. And here we get to see where different traces are coupled a little too tightly together. And actually, let's take a look here. Generally, like a general rule of thumb for coupling is you want to stay under 8% for your coefficient for your coupling coefficient. What does that mean? It's basically how strongly two traces are coupled to each other magnetically. So here we have this trace, right? This is this net and this net. They are next to each other and they run along each other's paths a little too closely together. I can get more granular with it by looking at my impedance, looking at my coupling table and pinpointing out those traces. Now, how do you know if you're in the danger zone as far as your coupling coefficient is concerned? Well, it depends on your project. In general, 8% or more coupling coefficient, unless that's intentional, can start to be a problem. So now that we see that these two traces have some coupling, let's take a look at how much crosstalk they're experiencing in the PCB. And that requires a slightly different process. So once coupling workflow is done, I'll go ahead and take note of the victim trace. It's known as the victim trace and the aggressor trace. The aggressor trace is this N25 trace, and then the victim trace is the Ethernet trace. Okay, that's problematic. I may need to move this out the way and see what I can do to fix this, but let's go ahead and save analysis results. And we have the aggressor net and the victim trace reference net. So what we should do is note these two traces, these two signal names, and we're going to analyze how much crosstalk is occurring between them. So with my analysis saved for coupling, I can go to crosstalk, that workflow. Now, I'm going to select my nets. I'm only wanting to select the nets that I care about when it comes to crosstalk. So I save those net names. Otherwise, if I get or try to get crosstalk for everything, then that's just going to make the simulation take forever. So, okay, so that is one of the nets. And just to make sure I am highlighting this, yes. So here was the red spot, red area. And then we have Ethernet or ETH underscore RX, put an asterisk around there. And this is RXCTL. So we want this net moved over and voila, it's highlighted. So now we'll choose apply, then okay. I'll enable distributed computing. I have 8 cores available to do this simulation. You can set your cut area options. I'm not going to do any of that. I'll just keep it as the modified settings and then start my analysis for crosstalk. So I did the crosstalk analysis, which lists the results in millivolts. You see how many millivolts are affecting, or like how many millivolts change or difference is being impressed upon a victim trace. So here I've selected my nets, and then we have Ethernet or ETH receive CTL, and this net ending in 3741. When we look at and to finish the analysis and view crosstalk visions, this is what it looks like. Okay, so we get a nice quick visual of what is being affected. When we look at the scale, you have your millivolts, and it seems that in this blue one, Ethernet is not being affected. We have 0 millivolts of crosstalk on Ethernet if this is considered a victim. But the crosstalk result is on this other net, N25693741, that is being affected by a good 10 millivolts. Depending on the signal, that may be unacceptable. I'm going to dig deeper into this. In the crosstalk tables down here, let's go into what this really looks like, what's causing this. So the victim receiver is this net here, all types of crosstalk. Let's show the details on this. So when I click on, like, say, the first one, okay, so we're looking at the nets that have crosstalk. The one in red has the most crosstalk on it. In blue, we are outside of the, more than 0 millivolt region. You see here in this blue, that is too low, but here we have 10.54 millivolts for this trace. So what we're going to do, this net 3741 is analyze this. It also has this name vmode_1. I'm going to click on here and then look at the waveform. So there are a number of waveforms here. What I'm interested in is the device as it comes out of this device here. Let's take a look at it here. In the results, it says U9, XU9. So we're going to look for that. We find U9, and we also have the other device, U5. So let me uncheck some of these. I'm interested in the traces that have issues. This one, it does. This is U2. And then to make this easier to see, let's go to property, change the width to something thicker and with a higher contrast on this canvas. Much better. So we're looking at, notice the behavior in the nanosecond response. They have the rise time, and ideally the signal would shoot straight up and not have any ringing, not have any noise, and then settle out, settle out immediately, or have a nice smooth curve that goes straight across. But look at this, there's interference from an aggressor trace that's affecting the signal and making the voltage oscillate. Eventually it does settle down and that's good, but we don't want any of this in the first place, especially on the multi-nanosecond range. That's 5 nanoseconds. That may be too long for some chips, for a number of chips. So, it really depends on your application. That could be fine. It may not be fine for receiving signals, signals being received on a chip. Let's look at another waveform. We have a real big problem here. So while this may be acceptable in some scenarios, this is not. So I'm going to click on here to make it easier to see and adjust the color. We do not want too much oscillation. Now, mind you, this is zoomed in. So we're still in the 2.5 volt range. If that's okay, then cool. But if we are not able to swing too many millivolts, then that's an issue, especially lasting from 1 to, especially lasting pretty much almost 9 nanoseconds here. When I was working at Intel, we had a situation where a PCB, well, yeah, let me talk to you. When I was working at Intel, we had a situation where our PCB we needed to get it down from 15 millivolts of noise down to less than 12 millivolts of noise. 3 millivolts made a difference, okay? Here, with this crosstalk and these fluctuations, you're dealing with 10 millivolts in some of these some of these traces, right? We have it here as well. I'm going to change that to a white background to make it easier. And then we also have this trace. This is in many cases can be acceptable. This is fine, but these may not be. And this might also not be, depending. If we have to stay strict within a certain voltage range, then that could be a problem as well, or it may not. So these are the kinds of analyses you want to do to make sure you really see what's going on when it comes to crosstalk. It can be very dangerous to not run simulation and verify. So depending on your noise budget, your millivolts you can handle, this may or may not be acceptable, obviously. Now, what are ways to fix it if it is too much of a problem? Well, first let's back up and get to the reason why this could be happening or makes it worse. First of all, traces that aren't supposed to be together being too close, the magnetic coupling causing crosstalk to happen, more crosstalk than we are comfortable with or should allow. 8% coupling or more usually start to cause some kind of issues you need to pay attention to. So the solution would be to move, one of the solutions would be to move the traces away from each other. That may be difficult to do in a high density interconnect, high complexity, highly dense PCB, understandable. What you can also do is set rules so that your two traces that are problematic, make it so that they don't run together for as long. So here, these two traces are running together a little too long. Let's look at the distance here. So if I measure from here to here, this segment to that segment, they're running together for at least 58 thousandths of an inch, 58 mils. Not good. We may want to reduce that to 30 mils or 10 mils, or just not have them close together at all. So I would move or slide this out the way, okay, if I can. I'd have to move things around and to minimize or eliminate that that proximity here so that there's less crosstalk. If I have some space, but it could still be a problem, I may want to add a guard trace in the design, right? So I may want to put in a guard trace that I can get in here. When I route this guard trace, then that trace can be something that has like a ground net to have a return path for those fields much closer than they would, because basically the nearest copper structure, the nearest conductive structure is this trace next to, well, is this trace here and this red one, and it's picking out those fields. So if you put like a guard trace, some vias and whatnot, or a copper structure like a polygon to capture that return sooner instead of letting those fields spill out and find their own path or route, then that's going to practically eliminate or at least reduce your field spreading anywhere. Once you start thinking about the fields and how they're routed, wherever it's a trace, a via, guard traces, blind or buried vias, it doesn't matter. Once you start thinking of copper structures and conductive structures as ways to guide the electromagnetic field as it propagates through dielectric, then you'll understand how the field can start leaking and go and find any return path it needs to have a return reference for its fields. The effects that we see, like crosstalk and noise, EMI, these are all the result of mismanaged fields. So crosstalk is actually very predictable, very predictable. And to see the details of how much crosstalk you're experiencing on your traces, you do that by verifying with tools like Sigrity X Aurora. Thanks so much for watching this video. Hope it's been helpful. Test it out on your PCB and see what results you find before you send your board out for fabrication.